In this video, I am going to discuss kinetic molecular theory, compressibility factor, deviation from ideal behavior, and Vander Waal equation. In the previous video, we have discussed ideal gas equation. So when we plot PV on the y-axis and pressure on the x-axis, you will get a straight line for ideal gas. That shows ideal gas obey Boyle's law at all the pressure range. But when we plot the same graph for other gases, for example helium, or hydrogen or carbon monoxide, you will get different curves. That means these gases obey Boyle's law at lower pressure range but disobey Boyle's law at higher pressure. In this video, we are going to discuss what are the qualities that make a gas ideal. To understand the qualities that make a gas ideal, scientists developed a theory named Kinetic Molecular Theory. In this theory, they made assumptions regarding how should molecules be and how should they behave to make a gas ideal. So let's see the assumptions of kinetic molecular theory. It is assumed that the ideal gas molecules are so small that they occupy negligible space. That's why they can be compressed into a very little space. There is no force of attraction between these molecules. That's why they can spread in all available space. These molecules are always in motion and their collisions are perfectly elastic. That means they do not lose any energy in collisions. When these molecules collide with the wall of the container, they exert pressure on it. On increasing temperature, kinetic energy of molecules also increases. That's why pressure increases on increasing the temperature. So which are the assumptions of kinetic molecular theory went wrong in case of real gases? So these two assumptions went wrong in case of real gases. First, it is assumed that ideal gas molecules are so small that they occupy negligible space. But in case of real gases, they possess some volume. The next assumption, that there is no force of attraction between the molecules, is also wrong. Because in real gases, they do have intermolecular force of attraction. So real gases are not like ideal gases. That's why they behave differently and show deviation from ideal behavior. Can we measure deviation? How much they deviate from ideal behavior? Compressibility factor Z defines deviation from ideal gas equation. So let's see what is compressibility factor. We know PV is equal to nRT is the ideal gas equation and PV over nRT is the compressibility factor and it is denoted by capital letter Z as PV is equal to nRT. When you take the ratio for ideal gas, you will get its value 1. So when we plot a graph, compressibility factor versus pressure, we will get a straight line for ideal gas as the value of Z is 1 for ideal gas. But for real gases, the value of Z is not equal to 1. For example, if we plot the same graph for helium, we will get this curve. And when we plot the another graph for hydrogen and carbon monoxide, we will get different curves. If the value of Z is less than 1, that means gas shows negative deviation. For carbon monoxide, you can see it shows negative deviation from the ideal behavior. But for the other gases, for example hydrogen or helium and some part of the carbon monoxide, it shows positive deviation as the value of Z is more than 1. For ideal gas, we know PV over nRT is equal to 1. And for real gases, we just have seen that PV over nRT is not equal to 1. On comparing both the equation, we come to know that nRT is same for both the equation. So you can cancel out nRT from both the equation and you will get the equation PV for ideal is not equal to PV for real. So why is the product of pressure and volume is different for real gases? So let's see. When we plot pressure versus volume, we will get this curve for ideal gases, and when we plot the same curve for real gases, we will get another curve. When we measure pressure for certain volume for ideal gas, we will get this value. And when we measure pressure for the same volume of real gas, we will get this value. On comparing both the values, we come to know that pressure of real gas is less than that of ideal gas. Similarly, when we compare volume of real gases versus ideal gases, for the certain value of pressure, when we measure volume for ideal gas, we will get this value. And when we measure volume for real gases, we will get this value. So here we can see volume of real gas is more than that of ideal gas. So let's see why is the pressure of real gases is less than that of ideal gas. Because there is an intermolecular force of attraction between the molecules of real gases. And these forces comes into action at shorter distance. So when we increase pressure, volume reduces, so the attractive forces comes into action. And when the molecule of real gases is about to collide with the wall, the force of attraction drag it back so it cannot collide with its full impact. That's why the pressure experienced by the walls of container is less than that of expected in case of real gases. While in case of ideal gases there is no force of attraction between the molecule. So molecule will collide with the wall of the container with its full impact and it exerts more pressure as compared to the real gas. Now let's see why is the volume of real gases is more than that of ideal gases. Molecules of real gases are not like ideal gases, they have some volume, while in case of ideal gases they do not possess any volume. In real gases, like attractive forces, there are repulsive forces too, and at high pressure when the molecular distance decreases, they also comes into action. These are the molecules of ideal gases. As they possess negligible volume and there is no force of attraction between them, they can be compressed to any volume. And these are the molecules of real gases. As they possess some volume and there is attractive as well as repulsive forces acting between them, they cannot be compressed further. So that's why they possess more volume as compared to ideal gases. So from the above discussion, we come to know that ideal gas equation doesn't fit for a real gas. To make it suitable for real gas, it requires some correction. So let's do first correction in the volume term. As we just discussed, volume of real gases is more than that of volume of ideal gases. So to make it equal to the volume of ideal gas, we have to subtract some amount from the volume of real gases. So here, volume of ideal gas will be equal to volume of real gas minus NB. Here, volume of real is the observed volume and NB is the correction term in the volume, where N is the number of moles, B is the Vander Waal constant and its value depends on the gas. Now let's do some correction in pressure. We just have discussed the pressure of real gas is less than pressure of ideal gas. To make it equal to the pressure of ideal, we have to add some term in the pressure of real gas. So here, pressure of ideal will be equal to pressure of real plus AN square over V square. Here, pressure of real is the observed pressure and AN square over V square is the correction term in pressure, where N is the number of moles, V is the volume, A is the Vander Waal constant and its value depends on the gas, and it is the measure of magnitude of intermolecular forces. So when we combine both the correction, we will get Vander Waal equation. Here PV over nRT is the ideal gas equation, and this equation is known as Vander Waal equation, where we include both the correction in pressure term as well as in volume term. So you will get the equation P real plus AN square over V square multiplied by V minus NB is equal to nRT. This equation is fit for real gases also.